So we mentioned, right, that the electrons quickly annihilate with positrons and turn into pairs of gamma rays that add to the thermal milieu inside the sun. The neutrinos fly out without interacting with anything. And so we can build neutrino detectors and see what conditions are like in the sun's core today and found fundamental things by doing that. And then I talked about how 0.7% of the mass that goes into the helium nucleus, the 4 protons, kind of disappears. And that's due to the binding energy of the helium-4 nucleus. And so these nuclear reactions are converted into mass into energy, and that's how the sun shines. Now, it's probably worth pointing out there's nothing magical about nuclear reactions converting mass into energy versus other types of reactions. In other words, it would be a lot harder to measure, but chemical reactions are doing that too, right? You take chemistry, and they drill into your head that the mass of the reactants is equal to the mass of the products. It's a bit of a lie. It's just harder to distinguish that. But if you combine chemicals together, they do an exothermic reaction, the products are a little bit less mass than the reactants. And it's that loss in mass that turns into the energy given off by the reaction. So don't be under the impression that only nuclear reactions convert mass to energy. No, chemical reactions do that too. You're biochemical. You're running via chemical reactions. You also are powered by converting a little bit of mass into energy. That's happening everywhere. But nuclear reactions do it more efficiently, and chemical reactions do it more. A fraction of the ingoing mass, so to speak, is converted to energy. I'll also mention, by the way, that it's not true that the mass of the sun diminishes every time we have one of these nuclear reactions, even though we're saying that we're converting mass into energy. Because that energy, as long as it's confined within the sun, shows up as part of its mass. In relativity, there really is this equivalence between mass and energy. And so the gravitational influence of the sun is due to its mass, but its mass also includes its thermal energy, the energy of photons within it, and so forth. An iron skillet that you heat up and give thermal energy to has more mass than it did before you heated it up. So the only thing that is, the way that the sun is really losing mass via these nuclear reactions is when the photons leave the surface. When the energy leaves the surface, it's the sun's radiating photons into space that represents the actual mass loss ultimately due to these nuclear reactions. So that's a subtle point to realize as well. What questions do you have at this point?
I did not understand. Don't you consider photons to be massless?
They are massless. However, remember, or be reinformed, or whatever you're going to call it, that in relativity, right, mass is not additive. In other words, we talk about the system mass in relativity, and that's not the sum of the masses of all the particles. The system mass also involves the momenta of the particles. Right? System mass squared is the sum of the energy squared minus the sum of the momenta quantity squared times c squared if we're using, or no, I guess, yeah. If c is 1, then the system mass squared is the sum of all the particle energy squared minus the sum of all the particles momenta squared. E squared minus p squared equals m squared, so to speak, applied to the system as a whole. And so, yeah, the photons are massless, but that doesn't mean that they don't contribute mass to the system of which they are a part, because they do have momentum, they do have energy. And while any individual photon is massless, they still are contributing to the system mass. So, yeah. What other questions do you have? Okay, so let's continue on our merry way here. Then I will point out more specifically the mass of that helium nucleus of, well, the mass of the 4 protons that went in, right? 1,1H is a proton because there's 1 particle in the nucleus and 1 proton. And sorry, the total number of particles is 1 and the number of protons is 1. It's a proton. Those 4 protons exceeds, mass of the 4 protons exceeds that of the 1 helium-4 nucleus, 2 protons, 4 total particles, so there's 2 protons and 2 neutrons in that sucker, by 26.71 mega electron volts divided by c squared. So it's more convenient to use MeV over c squared rather than kilograms because it would be a very tiny number of kilograms. So 26.71 MeV over c squared. That's the binding energy of that helium-4 nucleus. That's the energy associated with the strong nuclear force binding the protons and neutrons together. Representing the binding energy of the helium-4 nucleus. So this reaction, this being the reaction of a series of reactions we talked about before, turning hydrogen into helium, this reaction releases that much energy, 26.71 MeV per reaction. In the form of photons and neutrinos. Roughly, what's the mass of a proton or a neutron in energy units over c squared? Do you know that? What's the mass of an electron in energy units? Do you know that? It's a good number to know. Every physics and astronomy student should know the mass of an electron in keV over c squared.
Don't really keep, but it's directly using that.
No, that's a different thing. That's a different thing. Yeah, I'm not talking about like HC. I'm not talking about HC being 1240 eV nanometers, that kind of thing. I'm talking about the mass of an electron or a positron. Do you know? Do you know? Apparently not. The mass of an electron is 511 keV over c squared. If we were using natural units where c is 1, we would just say keV here. So 511 kilo electron volts over c squared is the mass of an electron or a positron. And the mass of a proton or a neutron is approximately, it's a bit less, 1 giga electron volt over c squared. The GeV over c squared is actually like 938 MeV over c squared for, I think, the neutron, and 937 for the proton, something like that. But they're both about a GeV over c squared. What's a GeV? What does giga stand for? What's giga? Okay, what's kilo? You're going to kill me if you don't know what a kilo stands for. Kilo is 1,000. What's mega?
10,000.
No. It's a million. So this MeV is a million electron volts. What's giga? Next one up. 1,000, million, billion. Yeah. So a GeV is a billion electron volts. So just, look at the comparisons here. The amount of energy it produces, is that a lot more or a lot less than the mass of an electron if we use natural limits, so we're just treating C as being 1. So 26.71 MeV, much more than, much less than the mass of an electron. Much more, right? How about a proton or a neutron?
Less.
Much less, yeah, much less. So it's about 0.7% again of the mass of the 4 protons that went in is converted into energy for each reaction. And if you run the numbers, take the sun's luminosity and divide it by c squared, that would be what? What would I get if I took the sun's luminosity and divided that by c squared, that amount of energy over c squared, what does that represent? What that represents the sun doing what? Yes?
Is the amount of mass lost per second?
Yeah, that's the amount of mass that the sun loses per second. It's luminosity divided by c squared is how much mass it's losing every second. If you put in the numbers, I don't have them right here, but if you put in the numbers, that corresponds to about every 5 seconds the sun converts the total mass of all the people in the United States into energy. About every 5 seconds or so. But the sun is very massive, and so that's not a very large fraction of its mass, but still, it's, that's what it's doing, essentially. Okay, so, let's see, 69% of the time in current conditions in the sun's core, 69% of the time, a helium-3 nucleus finds another helium-3 nucleus. That's the third and final step. Of the PP1 chain. All right, so remember that for the first step, 2 protons combine, what do they make? They make deuterium, right? They make a deuterium nucleus, plus they also spit out a positron and a neutrino. And then the second step is the deuterium does what? Combines with what? Remember? Do you remember? Can you go back on the notes if you want. 2 protons combine to make a deuterium. Deuterium has a very high interaction cross section. And so next in comes a proton, fuses with the deuterium to make a helium-3 nucleus. And then the final step is helium-3 meets helium-3 to produce helium-4, and it also spits out 2 protons. So 69% of the time, that's what actually happens is the helium-3 finds another helium-3, and you're done. You've made the helium-4 nucleus. But wait, there's more. 31% of the time it finds a helium-4 nucleus instead, and we get the PP2 chain. (31% of the time) a helium-3 nucleus fuses with a helium-4 nucleus instead. And we get the proton-proton Roman numeral 2 chain. This is a branch of the proton-proton chain that's not quite as common, but it's not uncommon either. So in other words, instead of the last step being helium-3 plus helium-3 makes helium-4, blah, 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 it's helium-3 plus helium-4 fused to form beryllium-7 plus a gamma ray. Then that beryllium-7 nucleus combines with an electron. By the way, just be sure you're following along. Beryllium-7, how many protons are in that nucleus? 4, because that's what the lower number represents. Beryllium's atomic number is 4. How many neutrons? 3, yeah, because there's 7 total particles, right? So the leftover must be neutrons. So beryllium-7 combines with an electron to make lithium-7 plus an electron neutrino. So what happened inside the nucleus? The electron combined with what to make a what? So we started out with how many protons? And we ended with how many protons? We started with how many neutrons? 3. We ended with how many neutrons? 4. So what happened inside the nucleus? That electron combined with a what to make a what? It combined with a proton to make a neutron and a neutrino. So in other words, inside the nucleus what happened was that a proton plus an electron became a neutron plus an electron neutrino. It converted one of the protons into a neutron. Is charge conserved here? What's the charge on the left side? 0, because protons and electrons have equal and opposite electrical charge. What's the charge on the right side? Also 0, because what's the charge on a neutron? 0, and what's the charge on a neutrino? Ain't none, so electric charge is conserved. This is cool, all right? What about baryon number? What's the baryon number on the left side? 1, because protons and neutrons have baryon number plus 1. What's the baryon number on the right side? 1, because it's a neutron, it has baryon number 1, so we conserve baryon number. And now, what's the other kind of number that gets conserved that I'll talk about here? Lepton number, in particular, electron-lepton number. What's the electron-lepton number on the left? 1, because electrons, the matter leptons have baryon number, lepton number plus 1. What about on the right side? 1 as well, because neutrinos, electron-type neutrinos also have electron-lepton number of plus 1. So, in other words, this is good to go. It conserved the relevant numbers, quote unquote, baryon number, electric charge, electron-lepton number. And then finally, that lithium-7 nucleus combines with a, what's that? 1,1H is that's a proton, combines with a proton, and it actually makes 2 helium-4 nuclei as a result. Because everything adds up, how many protons are on the left side? 4, right? 3 for the lithium, 1 for that proton right there, the hydrogen. How many protons are on the right side? Also 4, because each helium-4 nucleus has 2 protons, and there's 2 of them, so there's 4 neutrons. 4 protons. How many protons? How many neutrons are on the left side? How many neutrons? How many protons are in that lithium? 3. So how many total particles are in that lithium?
7.
So how many of them are neutrons? 4. So there's 4 neutrons on the left. How many neutrons on the right?
8.
Still 4, right? Because there's 2 in each helium nucleus, right? Got to remember, this isn't the number of neutrons, it's the total number of particles. That's the convention. So 2 protons, 4 total particles means 2 neutrons. Up or minus lower is the number of neutrons. So there's 2 times 2 neutrons, 4 neutrons, everybody's happy! And so, hooray, we made helium again, starting ultimately from hydrogen. We've done it again with the pp2 chain. Wow, we feel so energetic right now. The net reaction is always the same. It's still 4 protons combined to make a helium-4 nucleus. If you trace through, ultimately, 4 protons combined to make each of the helium-4 nuclei, but 2 of those protons turned into the 2 neutrons in the helium-4 nucleus in each case. So we've got PP1 and PP2, and there's a rarer side branch called PP3. Let's do PP3, shall we? 0.3% of the time. So, okay, the numbers don't add up to 100% because they're rounded off, right? So 0.3% of the time. The beryllium-7 nucleus captures a proton instead of an electron. And we get the PP3 chain. So we get all the way up to the beryllium-7 piece. In comes a proton, and it produces this nucleus, 8,5B. So first of all, what is B? What does that stand for? Do you remember your chemical symbols? What is B? What is it?
Boron.
It is boron. It is not boring, it is boron. And how many protons are in it? And how many neutrons are in it? 3. And it's the same over here, right? 1 plus 4 protons and 3 neutrons, right? And a gamma ray, gives off a gamma ray as well. And then that beryllium-5 nucleus, sorry, stop it. Boron 5, not even that, stop it. Boron 8 nucleus, right, because you named it like helium-4, 4 total parts. So boron 8 nucleus, it's not stable. It decays into beryllium-8 plus a positron plus an electron-type neutrino. Oh, but wait, so something in detail in the nucleus must have happened here. So we spat out a positron, so the charge on the nucleus dropped by 1, but the total number of particles is the same. So inside the nucleus, what happens in this decay? One of the what turns into a what?
Protons turns into a positron.
It doesn't turn into a positron. It emits a positron. It turns into a neutron by emitting a positron plus an electron neutrino. So in other words, inside the nucleus, we have proton becomes neutron plus positron plus electron neutrino. So charge is conserved, lepton number, electron-lepton number is conserved, because what's the lepton number of a positron? The electron-lepton number of what? What's the electron-lepton number of a positron? -1 and +1 for that. So the electron-lepton number is conserved. Everybody's happy. This can never happen outside a nucleus. A free proton will never do this. A free proton will not decay into a neutron. Why will it not decay into a neutron? What's more massive, a proton or a neutron? Neutrons are more massive than protons are. And so if you just have a proton sitting there, what would be the problem if I had a proton sitting there and then it turns into a neutron and spits out these two particles? What have I violated if the proton were to do this? Why is that impossible, given that neutrons have more mass than protons?
Energy conservation.
Yeah, you wouldn't be conserving energy here, right? You can't spontaneously decay into something that has more mass energy than you are starting with. So this is a no-no outside a nucleus. You can't have a free proton do that. But inside a nucleus, you can't, because it's part of a system. And so you can still conserve the system's energy. Here's a yes, yes. A neutron can decay into a proton, but I have to conserve everything. So in fact, a free neutron will do this. A free neutron is an unstable particle. When we get to cosmology, we'll talk about how in the early universe, neutrons were decaying into protons, and they would have all disappeared and left a universe of initially pure hydrogen if it weren't for nuclear reactions that bound some of the neutrons into helium nuclei and saved them, so to speak. And we can actually explain the overall chemical composition of the universe being about 3/4 hydrogen by mass and 1/4 helium by applying that principle in the early universe. But that's for later. But again, to try to develop your intuition for these reactions here. So the neutron became a proton. We're good for baryon number here. But we got to get the electric charge right. What's the charge over here? None. What's the charge over here so far? 1. How am I going to balance that out? An electron, right? So cool. An electron. Nice. But wait a minute. What's the lepton number on the left? 0. What's the lepton number so far on the right? It's 1. How am I going to balance that out? I need something with a electron-lepton number of -1. What will it give me? What's that? An anti-electron neutrino. That's right. An electron anti-neutrino. So you need a bar means anti-neutrino here. So you need a new bar E, or however you want to call it. So free neutrons will do this. They will undergo this decay with a half-life of something like 11 minutes. They will do that. I will point out that you can almost sort of do algebra on these things. In other words, you can move a particle to the other side if you replace it with its antiparticle. It's kind of like subtracting, so to speak. So in other words, here's another possible interaction. Neutron plus positron becomes proton plus antineutrino. That's what I meant to do. E plus, yes, thank you, yeah. Neutron plus positron becomes proton plus antineutrino, anti-electron neutrino. You can make all those different rearrangements like that. So I think that's kind of fun that you can move a particle to the other side and replace it with its antiparticle, and vice versa. You move an antiparticle to the other side of the arrow if you replace it with the particle.
So in reality, do they happen in a systemic way, or do they happen in all the possible ways?
So any of these combinations works, but some of them are much more likely than others. Yeah, but you can, so yeah, that's what it comes down to. You get to do it, but you also have to conserve energy here. So this can't happen because it doesn't conserve energy. But on the other hand, if I bring in an electron over here, it can happen if the electron has enough energy to make up for the mass difference. It has enough energy to account for the extra mass you need to create the neutrino. Sorry, for the neutron from the proton, for example. Yep. Okay, we should probably finish this reaction right here because we're not done yet. We don't have helium-4 yet. Beryllium-8 is an unstable nucleus. It spontaneously will decay into a pair of helium-4 nuclei. And we'll come back to this later. When the sun or other stars fuse helium into carbon, it's the triple alpha reaction where 3 helium-4 nuclei combine to form a carbon-12. Now, 3 particles coming together at the same time is extremely unlikely. So what happens is, first 2 helium nuclei combine to make a beryllium-8, but it's unstable. It will almost instantly fall apart again. And so only if another helium-4 comes in the nick of time and meets that beryllium-8 nucleus can they fuse to form a carbon-12 nucleus. And it turns out there's a resonance involved. That if that nuclear resonance were there, would mean you couldn't build carbon and we wouldn't be here. So thank you, laws of nature, for having that resonance. Okay. Here's another aside. Electrons are stable. There are 2 particles that are also leptons, but they're sort of heavy versions of the electron. Do you remember, or do you know, what's kind of the next mass up, so to speak? In other words, we've got electrons, and electrons are stable. They won't decay. But there's another type of lepton that's negatively charged just like an electron. It's got more mass than an electron. And if you can't tell me what it is, I'll have a cow. Which is kind of cool. Moo. Muons. Yeah, muons. Yeah. So, you're welcome. So, muons are a sort of heavy electron, not literally, but in other words, they are leptons, just like electrons are. And so there's the matter type muon, which is mu minus, and the antiparticle of that is the mu plus. It can decay. It's unstable. Muons will decay. In fact, one of the classic demonstrations of time dilation in relativity is cosmic rays create muons in Earth's upper atmosphere, and their half-life is, I forget, it's like 2.2 microseconds or something like that. And if you calculate how fast they're moving versus how long they take to get to the ground in our frame of reference, they shouldn't be able to make it to the ground because it takes well longer than their half-life in order to do it. But that's by our clocks. By the particles clock, it's ticking slowly. And so because of the time dilation, it is able to make it all the way to the ground as a result of that. So mu minus can decay into an electron. A muon can decay into an electron. Have we conserved charge? Is electric charge the same on both sides? But wait a minute. So a muon has a mu minus, a matter muon, has muon lepton number plus 1. true minus, its muon type lepton, its muon lepton number is +1, but its electron lepton number is 0. So over here, if we kind of list it here, right? So over here, I'm just doing this spontaneously, it's not going to know. So muon lepton number +1, what's the muon lepton number over here? I mean, I haven't told you what the muon lepton number of electron is, but guess what it is? What's the muon lepton number of an electron? It's 0, because it's not a muon. So this would violate the conservation of muon lepton number and electron lepton number. They both not be conserved because on the left side, we've got L mu equals +1, LE equals 0. So far on the right side, we've got L mu equals 0, LE equals +1. So we have to fix that. I need to add something to cancel out LE equals +1 for the electron. What comes to mind? What sort of thingy could I throw into this reaction to cancel out L equals +1 for the electron?
Anti-electron or an anti-electron type neutrino.
Yes, an anti-electron neutrino will cancel out the electron lepton number there. So now we'll be back to 0 for electron lepton number on both sides, but we're still stuck in terms of muon lepton number. What do you think I can add to fix that?
Muon type neutrino.
That's exactly what it is, yes. So we also have to have a muon type neutrino to balance muon lepton number. So this is the reaction that turns a muon into an electron, and it also has to give off a pair of neutrinos. One's an anti-electron neutrino, the other is a muon type neutrino. There are also tau particles, tau and anti-tau. We won't bother with those, but in other words, there's also tau lepton number. But we'll just stick with electrons and muons for now. So there's 3 families of leptons. There's the electron family, the muon family, and the tauon family of leptons. And they also, and this is just an aside, but I figured this is interesting to know. Okay, so, but well, before I get to that, because I'm just doing this as I go. So let's see. There's a positively charged muon, an anti-muon. It can spontaneously decay. What's it going to turn into? Instead of an electron, it's going to produce a positron. Yeah, it's going to produce a positron. And instead of an anti-electron neutrino, you're going to have a electron neutrino. And instead of a muon neutrino, you're going to have an anti-muon neutrino. And again, everything gets, the various numbers get conserved if you do that. Fun with particle physics. I actually think this is fun personally. And in fact, we've got quarks and leptons. Well, I don't know if I probably shouldn't go down this rabbit hole right now. Should I go down the rabbit hole or not?
I'd like to.
Okay, let's go down the rabbit hole. Okay, so, protons and neutrons are made of quarks, according to quantum chromodynamics. So, what did I say? A proton is a combination of two up quarks and a down quark. Two up quarks and a down quark. An up quark has charge plus 2/3, where 1 is the charge on the proton. So an up quark has 2/3 the charge on the proton. And down has charge minus 1/3. So what's the total charge on up, up, down? Plus 1, right? 2/3 plus 2/3 minus 1/3 is 1. So that accounts for the charge on the proton. It's the sum of the charges on the three quarks.
Is that 2/3 for one quark?
Yes, it's 2/3 for each up quark. Each up quark has a charge of plus 2/3. 2/3 that is the proton. Down quark has a charge of minus 1/3. So add them up and you get plus 1. The neutron is up, down, down. So two down quarks and an up quark. What is going to be its total charge?
0.
Yeah, 2/3 minus 1/3 minus 1/3, total charge 0, right? Okay, so that works out. So when neutron becomes proton plus electron plus an anti-electron neutrino at the quark level, you can view it as one of the up quarks spits out an electron and an antineutrino and becomes a down quark. So inside the nucleus, you view it as the up quark has turned itself into a down quark, more fundamentally. Does that make sense? That's the idea there. With a W minus particle, a weak nuclear force carrier particle, that itself decays into the electron of the antineutrino. And then similarly, if a proton turns into a neutron, then a down quark spits out a positron and an electron neutrino and turns itself into an up quark. And we've got our families. You've got, for the quarks, up, down, and for the electrons, good lord. The electron and its neutrino. And those are all kind of a family of particles, if you will. A happy family, generations. And then there is kind of a more massive copy, so to speak, of ones that are not stable. And so for the leptons, we've got the muon and the muon type neutrino. And you know what the quarks are for this family? Yes?
Is it strange and charmed?
Strange and charm, yep, strange and charm. And I don't remember which one is analogous to the up quark and which one's analogous to the down quark. I can't remember. But one of them has plus 2/3 charge and the other one has minus 1/3 charge. And I don't happen to remember which is which. It's on that chart back there, but I don't feel like walking back there. I'm pretty sure. Actually, I do feel like walking back there. Let's see. So I think it's on there. Yeah, right. So, yeah, the charm is the plus 2/3 and the strange is the minus 1/3. So, strange is the minus 1/3, is that what I said?
Yeah, strange is minus.
Strange is minus 1/3, so I should put them in the other order. Because I should put the strange under the downs because they're the ones that have minus 1/3 electric charge. So you got your charmed quark and your strange quark, and they have a color, you know, there's a property called strangeness and charm, basically, that they have. And then there's a third generation family, if you will, which has loser names, because there's what's the loser name that the loser particle physics community gave to them? Top and bottom. Okay, got it. Which one's which? Let's see. Top is 2/3, bottom is minus 1/3. Top, bottom, top, brownie face, bottom, brownie face, and then the leptons are the tau particle and the tau neutrino. What are the names that would have been winners had they been picked? Instead, if they had a choice, you got strange and charm. You know, that's a good name. That's whimsical. And then it was either, should we call them top and bottom versus truth and beauty. Truth and beauty. Obviously, those people went to some big state school and never took a humanities. They were not well-rounded people. Who would pick top and bottom instead of truth and beauty? No! If they'd gone to O, it would be truth and beauty, right? Who thinks it should be truth and beauty? Yeah, obviously. Who thinks it should be top and bottom? Oh, good. Good. Okay. And then, of course, you can put bars over everything, or, E plus, mu plus, tau, and this is, okay, I should say tau minus here, and there's antiparticles that are very good too. And so, the baryons are the 3 quark particles. What are the 2 quark particles? Mesons, yeah. And they consist of a quark and an anti-quark bound together. So, particle physics in a nutshell. You could do a lot more than that, but anyway. And you got all these up, right? So in other words, there's also tau lepton number and all of that sort of thing that has to be considered as well. Okay. What questions do you have? Oh my gosh, it's already time for a break. Just having so much fun here. It's time for a break already. Okay, let's have a break. Yes?
Going forward, some of the equations, photon and is.
Yeah.
I think it's a couple of so must be this one.
Yeah.
So how do you know it's a photon and
That's not easy. That's more like, it gives it off because it'll be typically it'll create the nucleus in an excited state, and then it decays to its ground state and spits out as a result of that. Yeah. Yeah, and I don't think there's ones where you're supposed to fill in a gamma ray. I think you're just told on those, if I'm not mistaken. I could be wrong. All right, so let's talk about the other way that stars confuse hydrogen and helium. There's the proton-proton chain and its various branches, 1, 2, 3. There's also the CNO cycle. In the sun currently, it's about 10% of the energy is generated this way. But in more massive stars, and the sun later, when it's fusing hydrogen into helium in the shell surrounding its core, after its core runs out of hydrogen, they fuse via the CNO cycle, which is a more complicated chain. I've never memorized it. This is what I just look at if I need it. But let's write it down so that you can appreciate its glory. So, in the sun currently, and more over time, the sun's core is heating up as it converts hydrogen into helium. And it's contracting, it's heating up, so more and more of the CNO cycle will show up because it operates more efficiently at higher temperatures. In the sun, about 10% of the energy is generated via the CNO cycle. The CNO cycle. CNO are chemical symbols. C is carbon, N is nitrogen, O is oxygen. It's the CNO cycle because C and O nuclei are showing up within the various steps. It's a cycle because, as we'll see, it's a catalytic reaction. In other words, in chemistry, a catalyst is when you have a reactant that is also a product of the reaction, so that it's recycled. Here we'll find that carbon-12 is a nuclear catalyst. It starts the cycle and it comes back out at the end. It's recycled. So, we start with a carbon-12 nucleus, 12,6C, fuses with a proton, 1,1H, to become a nitrogen-13 nucleus, 13,7N, plus a gamma ray. And if we put in the mean reaction time per nucleus again, how long will a given nucleus last on average before it undergoes the reaction shown? So mean reaction time per nucleus. This one, it's about 2.5 million years. So start the clock at any given moment. You've got a carbon-12 nucleus in the sun. Start the clock. On average, 2.5 million years later, it combines with the protons, make nitrogen-13. Is that long or short compared to the sun's age? Ooh, super short, yeah, because the sun's like 4.5 billion years old. Okay. How many protons in the carbon?
6.
How many neutrons?
6.
How many protons in the nitrogen?
7.
How many neutrons?
6.
Also 6, yeah, also 6. Everything's conserved here. 7 protons in all on both sides, right? And nobody's turned into a neutron or anything. However, nitrogen-13 is an unstable isotope, so the nitrogen-13 nucleus will spontaneously decay into carbon-13 plus a positron plus, what else do we need? So, what's the lepton number of the positron? The electron-lepton number. So, unless said otherwise, when I say lepton number, I shall mean electron-lepton number because I'm tired of always saying electron-lepton number. So unless we have any muons around or tauons around, I will just say lepton number, and it means electron-lepton number because did I mention I'm tired of saying electron-lepton number? What's the lepton number of positron? -1. So what do I need here to balance that out? What's going to give me -1? I mean +1. What's that? Yeah, an electron neutrino. So we're going to need an electron neutrino there. And the mean reaction time for nucleus is tiny. That's why I wrote there, so I don't even know what it is. I think it's because the book just said it's very small. I'm not sure. Anyway, it's super tiny. Nitrogen-13 is a very unstable nucleus. And so quickly, one of the blank in it turns into a blank and gives off a positron and a neutrino. Did a proton turn into a neutron, or did a neutron turn into a proton? Yeah, a proton turned into a neutron. 7 protons here, 6 protons here, same number of total particles. So yeah, so a proton turns itself into a neutron inside the nucleus. Okay, now carbon-13 can then combine with a proton and produce nitrogen-14 plus a gamma ray. That happens after about 10 minutes on average. That's how long a carbon-13 nucleus will last before it fuses inside the sun with a proton and turns into a nitrogen-14. What's our air mostly composed of? What's the most abundant thing in the air we're breathing?
Nitrogen.
Nitrogen. What's the most common isotope of nitrogen? It's that one. Nitrogen-14 is the most common isotope of nitrogen. So most of the air in this room is N2 molecules where the 2 nitrogens are nitrogen-14 atoms. Okay. So the nitrogen-14, though, in the sun, is going to combine with a proton. And it's going to make oxygen-15 and a gamma ray. That's going to take about 4 million years. That nitrogen will last for a while before it undergoes the next step and turns into an oxygen-15. Of course, these are just averages. Oh, but oxygen-15 is an unstable isotope, not long for this world. It decays spontaneously into nitrogen-15 plus a positron plus an electron-type neutrino. So again, we had a proton turning itself into a neutron. And that's a few minutes. Half-life of a few minutes. And then in about 20 minutes, that nitrogen-15 combines with a proton and creates a carbon-12 nucleus plus a helium-4 nucleus. So in other words, they combine and then they just kind of break apart into a carbon-12 plus a helium-4. So that nitrogen nucleus lasts about 20 minutes before this happens. And so, as noted, carbon-12 came back out at the end, which is why this is the CNO cycle, because the carbon's getting recycled. Carbon-12 now is free to start this whole sequence again. And the other thing is, in terms of the net reaction, notice that 1, 2, 3, 4 protons went in to form that helium-4 nucleus in the end. So the net reaction in all of these things is still that 4 protons combine to make a helium-4 nucleus. The details differ, but in the end, the net reaction is always the same. So the carbon-12 nucleus is recycled, so it is a nuclear catalyst. What questions do you have? But it's not recycled 100% of the time. Carbon-12 is slowly getting used by this reaction because it turns out 0.04% of the time, not much, but not none, 0.04% of the time, another branch occurs. That terminates in the production of nitrogen-14 and helium-4. So we don't quite recycle all the carbon. But what? Okay. Questions, comments, observations? Let's tell the story of why we wouldn't be here without quantum tunneling. Because without quantum tunneling, the nuclear reactions in the sun's core and other stellar cores would require much higher temperatures than we actually see, like 1 trillion Kelvin instead of like 15 million Kelvin or so. So we'd be living in a rather different universe, as it were. Of course, if there weren't quantum tunneling, there'd be many things that would change about the universe. Quantum tunneling is just part of it. But let's talk about why quantum tunneling is our friend in terms of nuclear reactions inside the sun. So first we'll make an estimate of how hot you'd need to have the sun be for protons to overcome their mutual electric repulsion and get close enough to feel the strong nuclear force. And then we'll say, but wait a minute, it happens at much lower temperatures than that. What's going on here? So, gee, I wish okay, so look if you have your notes that I handed out, look at there's a slide which shows a plot from the book that looks something like this. So, we've got R in Fermis, or femtometers. What is a femtometer? Do you know? Exactly right. That's 10 to the minus 15 meters. 10 to the minus 15 meters, which is on the order of the size of an atomic nucleus or a proton. It's about the radius, about the size of a proton. So this is proton-proton interaction energy, potential energy of their interaction. And I think first I will draw the curve and then I'll start labeling it. So it looks something like this. Yeah, okay. And actually, right, so the way we want to draw this is, there's 0 right there. Don't have it right where the axis is. There's 0 energy right there. So that represents their Coulomb potential energy when infinitely far away from each other. So if they're infinitely far away from another, their electrostatic, their Coulomb potential energy is 0. And then this is supposed to be up at about 60 MeV. So my axis label here will be potential energy as a function of R, the separation of the two protons, in MeV. So R here, to be clear, is the distance between the protons. Distance between the two protons. So what is the Coulomb potential energy for two particles, charges Q1 and Q2, as a function of the distance between them? What's the Coulomb potential energy? So I've got, there's Q1, here's Q2, there's the distance between them. Don't make me go tell Dr. Trees you don't know the answer to this. That's the force. That's the force. Remember that the potential energy is not 1 over R squared, just R, right? So it's Q1, Q2 over something times R. In SI units, it's, remember? What comes after the 4? What comes after the 4 pi? Epsilon naught. Yeah. 4 pi epsilon naught R, that's the Coulomb potential energy. So for two protons, I say U sub C for Coulomb would be, what are Q1 and Q2 for two protons? What's the charge of a proton? What symbol do we use for the charge on a proton? It's the same we use for the charge on an electron. The fundamental charge gets the symbol the charge on an electron is minus E, the charge on a proton is plus E, right? So this would be E squared over 4 pi epsilon naught R. And so this piece, this curve right here, what's that a plot of? This thing's just gently, asymptotically going to zero. It looks like this. That's a plot of the Coulomb potential. So the Coulomb potential goes like, what's its dependence on R? It goes like?
1 over R.
Goes like 1 over R. Yeah. So here's, this piece represents Coulomb repulsion. Goes like 1 over R. In particular, it's E squared over 4 pi epsilon naught times 1 over R. And so I could draw, so see what we do. Yeah, not too bad. 50, 40, 30, 20, 10. And this should really be down to about around minus 30-ish right there. So this piece is Coulomb repulsion. This piece is saying as the two protons get closer together, their electrostatic potential energy gets bigger and bigger because they're repelling one another. But once they get close enough to one another, they start to feel an attraction due to the strong nuclear force. Neutrons and protons all attract one another due to the strong nuclear force. It's called strong for a reason. It's stronger than the electromagnetic force is, but it's also short range. It essentially doesn't act over distances larger than around the size of an atomic nucleus. And so as a result, it doesn't play a role until the particles are very close to one another. So this negative potential energy at very small distances is due to the strong force attraction. Due to strong force attraction. So here's where I have to either remind you or tell you of the 4 fundamental forces of nature. What are the 4 fundamental forces of nature? Well, we've got the strong nuclear force, often just called the strong force. The next strongest, if you will, is the electromagnetic force. What comes after that? There's 2 more.
Weak force.
The weak force, the weak nuclear force. Yeah, and then there's the gravitational force. So gravity, which isn't a force according to general relativity, blah, 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 but it is an interaction. So we also still call it a force in that sense. So the strong and the weak forces are both strong, short-range forces because of the fact that their carrier particles have mass. But the electromagnetic force, which has massless carrier particles, and gravity, which we think also has massless carrier particles, though we've never seen graviton, they extend out to infinity, if you will. And so the reason why in our everyday life what we notice are gravity and the electromagnetic forces because they're long-range forces. 2 protons that are further apart than the size of an atomic nucleus only feel their electrical repulsion. They're essentially not at all feeling any strong force attraction to one another. So in other words, until they get very close to one another, the 2 protons will not feel the strong force attraction. So now, let's suppose, so if I were to send in a proton towards another proton from a large distance away, or let's work in the center of mass frame. So we've got two protons approaching one another, and if we're in the center of mass frame, they have equal and opposite momenta, so they have the same speed, they're approaching one another. We said before that because of the electrical repulsion, well, what will they be doing? If I shoot two protons at one another, they're electrically repelling one another, so what happens to their speed as they get closer and closer together? It keeps decreasing, right? And eventually, if it was perfect aim, in general they do something like that, but if it was perfect aim, they would momentarily stop and then reverse directions again. So if we want them to fuse, the basic idea is they have to come close enough to one another to feel strong force attraction and bind them together, because that strong force attraction can overcome their electrical repulsion. So they need to get close enough together to feel the strong force attraction and bind one another. And here's the rub. So classically speaking, if I have a particle come in, it's got to get over this barrier right here. Okay? So if I have a particle, if I have the two particles starting out from a large distance away from one another with some incoming kinetic energy, we can represent that by drawing a line on our plot, a horizontal line on our plot. There's the energy of the incoming protons. If I plot that energy as a function of r, why am I drawing it as a horizontal line? What's their total energy, potential plus kinetic, as a function of distance? Does it change? Does their total energy change? No, energy conservation. They have the same total energy. So this is the energy of the incoming protons. That's equal to their kinetic energy when far away from each other. All right. So this is a plot of U as a function of position, potential energy as a function of position. This is a plot of the total energy of the particles coming in, which far, far away is purely kinetic energy, because what's their potential energy when they're far, far from one another? It's zero when they're far away from another, because 1 over infinity is 0. So far away, their energy is 0. Their potential energy is 0, right? And this is when we're choosing to let U be 0 at R infinity. Remember that this choice for the form of the potential energy, what we're doing is setting it equal to 0 at infinity. There's always an arbitrary constant in the definition of potential energy. And if we define the potential energy to be 0 at infinity, that means we can just make it Q1, Q2 over 4 pi epsilon R. Does that make sense? Does that make sense? Far, right? The idea that this is the potential energy corresponds to defining the PE to be 0 when they're very far away from each other. The 0 of PE is when they're very far away from each other. If we could add a constant to it, why would we want to do that? But remember, only changes in potential energy matter. So where it's 0 is absolutely up to you. So, this, at this particular value of R, this would represent the particle's energy minus its potential energy, total energy minus potential energy. So the difference between these two curves, what's that equal to the particle? It's its total energy minus its potential energy. What is that? What energy is that in the particle? That's its kinetic energy, right? That's its kinetic energy. Should we call it T or K? K. I'll call it K, okay. Mechanics folks like to call it T. Students tend to be like, what do you call that T for? Okay, so we'll call it K. We'll make one another happy here. So that's K. So that's the kinetic energy. Okay. So what's special about this crossing point right here? What's true about the particle's kinetic energy at that point right there? It's zero, right? The difference between the two curves is the kinetic energy. So it's all over the place. Let's see. So K equals 0 at this R. Right there. K is equal to 0 at that value of R for our two particles. So in other words, and again, we're in the center of mass frame. I should put that, put this in here, let's see. Assume center of mass frame. Let's do everything in the C of M frame. And so what we think of this is we're using the reduced mass, essentially. So what happens is the particles start far away from one another, get closer and closer and closer. Kinetic energy is getting smaller and smaller and smaller and smaller. We get to this, for this value of energy, this particular value of R right here. The particles momentarily stop and then what? They fly back out again, just the way they came in, right? So in other words, making a movie, it'd be like, first you're going to the left, slower and slower and slower, and then you bounce back to the right and just speed away from one another by the repulsion after that. So this R is called the classical turning point. The classical turning point, meaning it's where the two particles would turn around and fly away from one another. So, for this energy, will the protons fuse with one another in our classical model? Do they ever get close enough to feel the strong nuclear force? They do not. Okay? How about now, if this is the energy line, if this is their far away kinetic energy? Do they fuse? No. How about now? 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 They do it, yeah. So this is the borderline right there, right? In other words, the incoming KE, when they're far away from one another, has to be equal to the maximum height of the Coulomb barrier before the nuclear attraction takes over. This would just shoot up to infinity if we let it, but the nuclear reaction takes over, overcomes it, and makes it an attraction instead of a repulsion. So classically, we need this much energy to get them to fuse. So what we're going to do is some calculations that shows that it ain't going to happen, essentially. That the temperature we need is much higher than we observed inside the sun. What questions do you have? Drawn a lot there. So after having described all that, let me write some stuff out here. So now let's let it, it's not even protons anymore, it's just two nuclei with the same or even different numbers of protons. Let's be generic here. So consider a nucleus of charge Z1e so Z1 is the atomic number of that nucleus. So if it was a proton, what's Z1? 1. If it's a helium nucleus, what's Z1? 2. If it's a carbon nucleus, it's 6, and so forth. That's the number of protons. And each has charge E. So note carefully, the charge on an electron is minus E. We get the E from the idea of electron, but E is defined to be a positive quantity. So a proton has charge plus E, and an electron has charge minus E. And it's not based on the natural law, I'm sorry, it's a different E, okay? So we got a nucleus of charge Z1e, that collides with a nucleus of charge Z2e, such that a nuclear reaction takes place. For this to happen, they need to overcome the Coulomb barrier. At its highest point, just before the strong nuclear reaction, the strong nuclear attraction takes over. And because we love the equivalent one-body problem, we'll use it here. As usual, we can replace our two-body problem with an equivalent one-body problem in which a particle having reduced mass mu mu sub m, mu sub m, so we know it's not a muon pair, mu sub m approaches a fixed potential at the origin. A fixed, if you will, potential well at the origin. Center of the origin. So we just think of a single particle coming in and it's just approaching this thing that's locked in place representing the repulsive electric charge and strong force attraction of the two particles for one another. Catch up. You're still writing, so I have to keep waiting. So let's look at this classically. Classically, the distance of closest approach which we'll call R subclassical, classical turning point. So the classical turning point, we'll call that value R sub CL, is given by, okay, well, what would it be given by? So far away, its energy is all kinetic, no potential, right? By the time we're at the classical turning point, how much kinetic energy is there? None. So what do we know about the relationship between the potential energy at the classical turning point value and the kinetic energy when they're far away from one another? How should those compare? They should be equal, right? Because we would say that kinetic energy at infinity plus the potential energy at infinity, right? That's going to be, what's the potential energy at infinity? Zero, right? So the total energy of the incoming particle is the kinetic energy at infinity plus the potential energy at infinity. But that's zero, the potential energy at infinity. It's equal to the kinetic energy at R classical plus the potential energy at R classical. What's the kinetic energy at R classical? Zero, because that's where they're going to turn around. That's where they're not moving anymore. And so we know that E equals K infinity. That'll be 1/2 mu sub m v squared, where v is their incoming speed. Their speed far away. The far away speed of approach is equal to the potential energy at the classical turning point. That will be Z1, Z2, E squared over 4 pi epsilon naught R subclassical, because the two charges are Z1E and Z2E, so Q1, Q2 is Z1, Z2E squared. That's the product of the two charges. And the R is R classical in this case, so over 4 pi epsilon naught R classical. So this lets us figure out, okay, how fast do they have to be shot at one another from far away? Well, this would say, if they're shot at one another from far away at speed v, here's how close they get to one another. This is the classical turning point. And so, for any v, we could figure out what the classical turning point is, and we need it to be where they'd be close enough to feel the strong force interaction. Does that make sense? Not make sense? Okay? That's the idea, that's what we're setting up here. So now, I don't know about you, but boy, am I looking forward to continuing next class. Exclamation point. If you're writing that down, gotcha. We'll turn that into a temperature by saying, oh, but we know the relationship between the temperature and how fast the particles are moving on average.